Hello, welcome to Wildcat Science with Mrs. Haugo. This is chemistry and we're in chapter 11, Stoichiometry. And today we're going to do 11.4, solving stoichiometric problems. So please find your book and open up to page 353. We're going to be discussing what you read. So let's look at this diagram first. So this is a good diagram on page 353 to follow when you're doing problems. So you could follow the flowchart for each question, like mass to moles of product to mass of the product, or whatever part you are in. And then if you write out what you know, and you're going to repeat the same sequence of steps each time, so that's good to notice that what steps you do. And then as you're doing this, explain the meaning of your answer. What did you find? Try not to think of your answer as just a number, but as a quantity that represents something meaningful. So this is something we'll do in class, like did I answer the question? Does it make sense? And putting that in context. Oh, that's about the size of a balloon of hydrogen gas, or something like that. And then remember to practice examples without your notes, because that is easier. It might be harder than you would think to do it without your notes. So looking at the flow chart, mass of the substance, and if we're going from mass to moles of the same substance, remember it's 1 mole over the molar mass. And then to go from moles of one substance to moles of another substance, we're going to be using our mole ratio, which we found from the balanced chemical equation. And then when we're going from moles of the product, or a separate substance, to mass of the substance, we're going to be timesing that by the mass over 1 mole. Next up, we're going to be discussing calculating the limiting reactant on page 354 to 356. So please do make sure you're following along. Okay, so this problem is lithium metal reacts directly with nitrogen gas to produce lithium nitride, according to the balanced chemical equation. 6 moles of solid lithium reacts with 1 mole of nitrogen gas to form 2 moles of lithium nitride, which is solid. When 48 grams of lithium reacts with 46.5 grams of nitrogen gas, which reactant is the limiting reactant? So lithium is the only group 1 metal that is capable of reacting directly with nitrogen gas, which is fun to know, but not necessarily important for our limiting reactant. So what is the problem? Limiting reactant. And we're given the grams of lithium and the grams of nitrogen. And then things we would have to figure out are moles of each reactant, the molar mass of each reactant, and the mole ratio between lithium and nitrogen. So what is the first step in our limiting reactant problem? That is to find how many moles of each reactant we have. So looking through the problem, we have 48 grams of lithium divided by its molar mass. We have 6.92 moles of lithium is what we have. And for nitrogen, our original quantity times 1 over our molar mass, and we have 1.66 moles of nitrogen. So what is the second step in solving a stoichiometric limiting reactant problem? It is finding the mole ratio to determine the amount of moles needed to react. So we take 6.92 moles of lithium that we have, and we pretend it all reacts using our mole ratio, and we find out we have 1.15 moles of nitrogen would be needed if all of our lithium reacts. Given that amount of information, is nitrogen the limiting reactant or in excess? So if you said that nitrogen is in excess, you were right. So what we normally do is we normally calculate both of them before deciding. So the second reactant, nitrogen, we had 1.66 moles of nitrogen we have over our mole ratio, moles lithium over moles nitrogen. which means we would need 9.96 moles of lithium. So we see that we need 9.96 moles of lithium, but we only have 6.92 moles of lithium. So we don't have as much as we need, so lithium is our limiting reactant. So part 2 of the question is, how much lithium nitride can be produced from this reaction? So it's asking for the amount of product, and we know lithium is the limiting reactant, and some things we know are the molar mass of lithium nitride is 34.83 grams per mole, and the mole ratio between lithium, our limiting reactant, and the product is 6 to 2. So my question is, what are the steps to calculating the mass of the product now? So if you said first, we're going to take our moles of our limiting reactant and times it by our mole ratio, you would be right. And we normally do this in one line, but they did it in two, because then after we do our mole ratio, we would do our molar mass of our product, and there would be a fraction bar there. And we would get 80.46 grams of lithium nitride. The third part of this question is calculate the percentage yield of an experiment that actually produced 62.5 grams of lithium nitride. So it's asking us to find the percent yield, and we know actual yield is 62.5 grams lithium nitride, and our theoretical yield is 80.46 grams lithium nitride, which is right here. And then relationships are the formula for percent yield. So my question is, what is the percent yield? So if you set up your equation, percent yield equals actual over theoretical times 100, and then below that, percent yield equals 62.5 grams over 80.46 grams times 100, and that gave you 77.7%. You would be right. And then the book has another question, if you're following along. There is an experiment and 3.50 grams of ammonia react with 3.85 grams of oxygen in the balanced chemical equation. 4 moles of ammonia gas react with 5 moles of oxygen gas to produce 4 moles of nitrogen monoxide gas and 6 moles of water vapor. So looking at the question, which reactant is the limiting reactant? How much of the excess reactant remains after the limiting reactant is completely consumed? So it is asking us for limiting reactant and excess reactant. And we know the molar mass of ammonia is 17.03 grams per 1 mole. And we know the molar mass of oxygen is 32.0 grams per mole. And our mole ratio is 4 moles of ammonia over 5 moles of oxygen. So my question is, in a limiting reactant problem, what is the first step we should do? If you said figure out the moles, convert each of our reactants into moles, you would be right. So 3.5 grams of ammonia times 1 mole over its molar mass is equal to 0.206 moles of ammonia. That's how much we have. And 3.85 grams of oxygen over 1 mole over 32 grams is equal to 0.12 moles of oxygen. That's how much we have. My next question would be, what would be our next step in a limiting reactant problem? If you said to take the moles of each reactant and then pretend they all react and see how much of the other reactant we would need, you will be correct. So we have 0.206 moles of ammonia times its mole ratio would be 0.26 moles of oxygen would be needed to make all of that react. And we have 0.120 moles of oxygen times our mole ratio would be 0.096 moles of ammonia are needed. Okay, given that information, which one is our limiting reactant? If you said that oxygen is our limiting reactant, you would be right, because we have 0.120 moles and we need 0.26, so we have less than we need, so this one is our limiting reactant. The next question is, how do we figure out how much of our excess reactant is in excess after all the limiting reactant is gone. So if you said subtract them, you would be right. So we know ammonia is our excess reactant, and we know that we have 0.206 moles of ammonia, and we need 0.096 moles. So we subtract them, and we would have 0.110 moles of ammonia left over. And then if we were to convert that in a mole to mass problem, that would be the same as 1.87 grams of ammonia are left over. So oxygen is our limiting reactant in this problem, and there's 1.87 grams of ammonia left over. Okay, on the next page you can see stoichiometry with solutions, and this is an extension that we will talk about if we have more time once we talk about solutions in chapter 9. Our stoichiometry and nature is our chemistry connections found on page 358 and page 359. So you want to make sure that you're there in your book. And please write down stoichiometry and nature and sustainability and stoichiometry. Please write that down. So some important aspects of this, looking at our book, is knowing how much of a chemical is used or released when we're looking at chemical reactions that happen in our everyday life. Also important is the combustion of coal. Okay, your book looks at the balanced chemical equation of coal and oxygen, makes carbon dioxide, water, and sulfur dioxide. And it also points out that in 1 ton of coal, there's about 600 kilograms of carbon. And looking at our mole ratios, for every 1 mole of carbon dioxide made, we used up 1 mole of coal. So that would be about 3 times as much because the carbon dioxide has a greater mass than the carbon. So 1 mole of coal will relate to about 1,800 kilograms of carbon dioxide put into the atmosphere. Excuse me, I should have said 1 ton of coal will relate to 1,800 kilograms of carbon dioxide being released into the atmosphere. Also important in this section is stoichiometry and climate change. Page 359 goes on to talk about how higher levels of carbon dioxide in the atmosphere contributes to climate change. As we know, CO2 is a greenhouse gas, and so the more carbon we take from inside the ground that's been there for millions of years and then burn it and put it in the atmosphere, the more we change things. It also goes on about sequestering carbon through photosynthesis. So trees and plants will take carbon dioxide and through the process of photosynthesis make it into glucose, which then again is part of the food web. And that concludes our chapter 11 notes. All right, good job everybody.